Let's use this Tektronix Realtime Spectrum Analyzer to discover, trigger, capture, and analyze various characteristics of this RF signal. So we're just looking with the normal spectrum display, the center frequency at 2.4453 gig, and a span of 10 megahertz. This looks like just an ordinary CW unmodulated signal. But let's add the real-time display, or DPX display, which can do up to 3 million spectrum measurements a second. And with this display, we can actually see there's a low-duty cycle transient event that's occurring that is almost impossible to see on the spectrum display, and also almost impossible to see on a conventional spectrum analyzer. Even if we add a max hold trace, it may take several minutes to capture some evidence of this transient event. Let's take a look at what DPX, or the real-time display, can show us. This display is essentially comprised of tens or hundreds of thousands of spectrum measurements a second or more laid on top of each other and then color graded to show the density or frequency of occurrence. So in this case, the colors that are approaching red here are areas that are occupied most often, and as you work your way down through the yellow, the green, the light blue, and the dark blue, we're seeing the less frequently occurring things. So we can tell by looking at this display and understanding how it's being built that the signal that we're looking at is momentarily leaving this center frequency. And I can tell that because I see some noise popping up in this area here momentarily. If we look really carefully, we can see that we're finding a new frequency to sit at a little more often than not. In fact, if we go add a little bit of persistence to this display, we can see that a little bit clearer. So we can see when this signal leaves this center frequency, it's finding another frequency to sit at a little bit longer than anywhere else. And if we look a little more carefully, we can even see that when this signal is moving over to here, we're overshooting a little bit and then settling back out. And then when the signal returns back to the center frequency, it undershoots before it returns back to the center frequency. And that's one of the ideas with this DPX, or real-time display, is to show you live what's going on in real time and to give you a nice intuitive feel for what's happening with this signal over time. And with that knowledge, you can more intelligently apply a trigger to capture the particular event. Now, during the same time, we've been capturing that max hold trace, and I can actually see some evidence of this transient activity now captured in that max hold trace. But now, which one of these displays is really giving me a more intuitive view of what's happening with that signal? So now that I've discovered a little bit about what's going on with this signal, say I want to trigger on that so I can capture it into memory. What we'll do is bring up the trigger engine here, and one of the trigger types that we have is something called a frequency mask trigger. We could take advantage of the fact that the spectrum analyzer is computing the spectrum continuously live, and we can then compare that against a mask. So for example, if I bring up the positive peak trace on that real-time display, I can see that infrequent event going on here. Let me start with a new mask, and I quite literally can click and drag and move points around, right-click and add more points, or even automatically draw a mask around a trace. But in our case, I'm going to start with a new mask, and I want to trigger when the instantaneous spectrum of the signal comes up over into this area over here. So I'm just going to adjust a couple of points on the mask over here, get this one up out of the way. So now my trigger condition is going to be when the instantaneous spectrum hits that mask. I'll say I'm done editing the mask, switch myself from free run to triggered, and now if we take a look at the yellow spectrum trace, we can see we're capturing data and computing the spectrum when that instantaneous spectrum is crossing that mask. Now from a debug standpoint, one other very important thing that's happening is each time the instrument is triggering, I'm also sending a trigger output pulse out of the BNC connector on the front panel. This allows you to then trigger an external piece of equipment like a scope or a logic analyzer or something like that, so you can actually then correlate measurements and captures and acquisitions in other instruments that are coincident with this transient RF event. So now that we're triggering on this signal properly, let's go capture some of this over time to understand the behavior of this signal now over time. So I'm going to add a time overview display that allows me to control how much time I'm going to grab and what portion of that I want to go analyze. And let's also add a spectrogram display and a frequency versus time display. So with each of these displays added, the first thing I'll do is make some adjustments in my time overview. I know that I need to capture about 500 microseconds worth of time to capture this particular event. So what we can see in the time overview display is amplitude versus time. So the signal power is never changing. So we know the signal is just staying up at the same power and just moving in frequency. The frequency versus time plot down here shows me the instantaneous frequency deviation versus time, with the center of the plot being equal to the center frequency of the analyzer. So you can think of this as an FM demodulation view. The trigger location is indicated in each of the time domain displays. Now let's say I want to grab a little more data before the trigger occurred. That's controlled by this offset value. I can literally just change the number, or I can just grab the edge of the curtain here and drag it over and grab a little more pre-trigger information to center up on that event. So now I can see some pre-trigger information, then when the signal is actually hopped in frequency and then settled back out again. The spectrogram is built by computing spectrums over time during that same time period. In fact, it's helpful to stop this and take a look at what happens if we add a marker. If I add a marker into this display, I can move that marker around in time, and we can see that marker moving in every window. This allows me to correlate amplitude changes over time, frequency changes over time, and then even spectrum changes over time. In fact, if you look at where the marker position is here, we're lifting a spectrum trace out of this stack of spectrums and showing it to you down on the spectrum display down below. In fact, as I move this marker through time, we can literally see the complete seamless spectral history of this signal over time. So this is one quick example of how you can use a real-time spectrum analyzer to discover what's going on with your RF signals, see all the transient events and things that are going on, and get an intuitive feel for what RF signal is doing. Then intelligently apply a trigger to capture that particular event into memory and go look at it in multiple domains.
Find out more at Vicom's website.